An infinite series is a sum of infinite length. But what does it really mean to add infinitely many numbers together, and how can we understand it? Before we answer those questions, we first start off with some basic notation. This notation is known as summation notation. It is shorthand for adding a bunch of terms together. The sum symbol is the Greek letter capital sigma. We call the letter K a dummy symbol, meaning that it has no inherent meaning and we can change it out for any other symbol that's not in use. For example, all of the following sums are the same. The dummy symbol is just a placeholder for the symbol that will be replaced by numbers when we write out the sum. We cannot change the m or the n because that would change the starting and ending point for the sum. The individual terms of the sum are called summands, and they can be complex mathematical expressions. Just remember that the sigma tells you what values the dummy variables will take, and you simply substitute them in and add the results. Here is an explicit example of summation notation. Since the summation goes from 0 to 4, we know that we will have terms starting from k equals 0 going up through k equals 4. In each term, we just substitute explicitly the value of k that we happen to be on. All of this is fairly intuitive until we introduce infinite sums. Since we can never actually add up infinitely many terms, we need to find a different way of understanding this. Instead of using infinite sums, we'll just use an infinite list of finite sums. This is known as the sequence of partial sums. Consider the sum from k equals 1 to infinity of a sub k. Instead of taking the whole sum at once, we can take the first n terms for different values of n. When n equals 1, we have just a sub 1. When n equals 2, we have a sub 1 plus a sub 2. When n equals 3, we have a sub 1 plus a sub 2 plus a sub 3, and so on. We can call the first sum s sub 1, the second sum s sub 2, and then s sub 3, s sub 4, and keep getting values s sub n for every value of n. This gives us an infinite sequence of terms. This sequence s sub n is the sequence of partial sums. If the sequence converges, then we say the infinite series converges, and it converges to the limit of the sequence of partial sums. In other words, we have the following equations. Although we will use equal signs with infinite series, we need to remember that the underlying process is taking the limit of a sequence. The reason this is important is because now that we have infinite series framed in terms of sequences, we can apply our knowledge of sequences to this new situation. For example, if all the summands are non-negative, the resulting sequence of partial sums is an increasing sequence. This means that the sum must either converge or it must diverge to positive infinity. This means that the sum is always defined in this case, and it gives us the following important definition. Definition: the series sum of a sub n is said to be absolutely convergent if the sum of the absolute value of a sub n converges. We won't see any applications of absolute convergence in this class, but it turns out that absolutely convergent series are very nice because we can rearrange the sum in any way and it won't change the limit. However, there are series that are known as conditionally convergent, where rearranging the sum does change the value, which makes those sums much more difficult to work with. Here's a useful property that we get from our knowledge of sequences. Definition: we say that a series sum of a sub n satisfies the Cauchy criterion if its sequence s sub n of partial sums is a Cauchy sequence, so that for every epsilon greater than 0, there exists a capital N such that little m greater than capital N imply s sub n minus s sub m is less than epsilon. We use the Cauchy concept for sequences because it's hard to know what the sum is going to converge to. If we rewrite this in terms of the summands instead of the partial sums, we get the more common form of the Cauchy criterion. Definition: we say that the series sum of a sub n satisfies the Cauchy criterion if its sequence s sub n of partial sums is a Cauchy sequence, so that for every epsilon greater than 0, there exists a capital N such that little n greater than or equal to little m greater than capital N implies that the absolute value of the sum from k equals m to n of a sub k is less than epsilon. Although the second form looks quite different, it's actually the same thing. All we do is we substitute the partial sums in explicitly and then do the calculation. Once we have convergence defined in terms of Cauchy sequences, theorems that we've already proven give us information about infinite series. For example, theorem: a series converges if and only if it satisfies the Cauchy criterion. This follows by definition and the fact that a sequence converges if and only if it is a Cauchy sequence. A corollary of this is that if a series converges, then the limit of the summands is equal to 0. In class, we're going to take a look at some theorems that are related to the convergence of series, including several that you've already seen in calculus.